on this computer. We are recording. Okay, so again, today's lab, the focus of today's lab is confidence interval construction in R. And to demonstrate this, we're going to be working through a number of questions from the demo files. So that's questions 16 through 19 or 16 through 20, I believe. Now we're going to be picking apart different sub questions or different parts from these major questions. There are two data sets that are associated with this demo file. The names of those data sets are Doctor Exercise Demo, okay, and two, the second one is called Allen's midterm data. Okay, and those files are available in the lab demo folder or the demo data file folder on the course website. So we're gonna need those for questions 18 and 19. And then, oh, I guess we could also do 5% significance level, 5% significance level, 5% significance level, 95% interval. We might even be able to do question 20. We'll see how much time we have left, but it's somewhat redundant. So we'll focus on 16, 17, 18, and 19 for now. And then if there's still time and you guys want to see more examples, we can work through that. Okay, so the topic for today is confidence interval construction. Okay. And we have two types of confidence intervals that we're going to be working with. Okay. So we have Z score based interval, and then we have T value based interval. Okay, so first, a couple of little things about the intervals themselves. For each interval, we have a set of assumptions that we need to check before we actually start working through and constructing the intervals. The assumptions are very similar. So in the case of both intervals, the first assumption is always was a simple random sample collected. So I usually just designate that as SRS. So do we have an SRS from each sample? In the second assumption, we have for the Z score based interval, we have X bar is normal. And then for the student T, we have a slight twist on this, which would be sample from normal population. Okay, finally, we also have this. Not everyone writes this as an assumption. I usually write it down as an assumption just so we have it as like a checking point, like, okay, this is something we need to look out for when we're building the intervals. So that would be in the case of the Z-score formula, sigma is known. And in the case of the T-based formula, it would be sigma unknown. So the big differentiator between the first interval type, so the Z-score based interval, and the second interval type, which is the T-value based interval, is actually the third assumption. So a lot of the time in 151, we establish a rule, which is if sigma known, use Z-score. If sigma unknown, use a t-value. Okay. So that third assumption is one of the more critical ones because it in almost every case that you guys will see, this will be the differentiator between if I use a t-value approach or if I use the z-value approach, z-score approach. Okay. All right. Now, in terms of construction, the two intervals are built in the exact same way. So for the z-score formula, we find what is called a z subscript alpha over 2. And then for the t-based formula, we find what is called t alpha over 2 comma n minus 1. Okay, so the same idea. Basically, we're finding a z-score if we use the z-score formula, and then we find a t-value if we're using the t-value based formula. And these will be the general sort of designators of the information that is included with that z-score and with that t-value. So with the z-score, we just have area to the right of the score. With the t-value, we have area to the right of the t-value and what is called degrees of freedom, which is calculated by taking n minus 1, so sample size minus 1. All right, on step 2, we have computation of the formula. So we have compute x bar plus or minus z alpha over 2 multiplied by sigma over the square root of n. And then here we have S1 and then we have S2, which in this case is going to be compute x bar plus or minus, and now we have a t value multiplied by little s over the square root of n. So notice that the differences between the two intervals are very subtle. For the z-score based one, we have sigma, so we have a z-score. For the t-value based interval, we have little s, where the sigma is in the other formula, and then we have a t-value where the z-score is. So the general formula is actually identical, or the structure of the formula is identical, but the values that we're plugging into it change based off of what we know. So when we have sigma, z-score, when we do not, t-value. All right, and then finally, in each case, on the third step, we interpret. And that's consistent for both procedures. All right, now some of you that are in the lab today, we have 8 students now. So some of you guys may have seen the t-values already. I know that if you were in my section this morning, you would have saw the t-value, the t-table, and some illustrations of how to find t-values. If you haven't seen this yet, you will see it in lecture. I'm not going to spend a lot of time showing you. I don't think I'm going to show you how to do it via the tables in lab today. We'll just work on doing it via Rcmdr because that's sort of the purpose. And then I'll leave that particular subset for lecture. So you will see this from a table point of view. So you can find t-values in a very similar way to how you find z-scores based off of a new table. Or you can find t-values using Rcmdr, which is, in most cases more accurate, the same way that we learned how to find z-scores. And we're going to work through this type of material today. All right, so basically, again, our focus is on constructing confidence intervals. As we work through the problems in the demo files, we're going to be basically distinguishing between these two scenarios. So should we use a z-score or should we use a t-value? Okay, and then we're going to look at different ways of building the interval, sort of more brute force or a more computationally intensive way, and then a more computational way where Rcmdr basically just spits the interval out for us. All right, so before I flip over to the actual Rcmdr screen, does anyone have any questions about what we're going to work through? All right. I am seeing none. Okay, so I'll leave this active for now. All right, so now we flip over. So share screen, desktop 1. There we go. Okay, so here's our demo data file. And we are starting with question 16, which is shown below. Okay, so we have a random sample of 1,280 students is taken from a larger population, and it reveals that the sample mean amount for their student loans is $18,900. Pretty hefty. Suppose it is known that the standard deviation sigma of the population is 40,220. So this is kind of insane, actually, when you think about it. Like your average is about 18,900, but that varies by $40,000 around the mean, which implies that the amounts in loans, there must be a lot of zero values, and that there are values, as high as what would be around 60,000. So this distribution is almost certainly skewed, as financial data tends to be. Okay, and we want to find a 90% confidence interval for the population mean. So that's the goal of our problem. All right, so part A, what do you know about the mean, standard deviation, and shape of the sampling distribution of X bar? Why do we know the sampling distribution has the indicated shape? So this part A is actually kind of a throwback question to the previous unit. So first off, what do we know about the population mean? Well, as you can see here, because this one is actually filled out, it's unknown. So we don't actually know anything. There's no information given to us in the problem about the population mean. There's no indication of what it might actually be. We have an estimate, but we don't know where the actual value lies. What about the standard deviation of X bar? So that's sigma over the square root of n. So this is equal to 40,220 divided by 1,280, which is 1,124.24. So for a sample size of 1,280, we have a standard deviation of 1,124.24. What is the approximate shape of the sampling distribution? It's normal. Why is that true? Because the sample size is much greater than 30. So the central limit theorem takes over in this case. So this first part is essentially just a review of what we worked on last week. Okay, so now calculate a 90% confidence interval for the population mean. Okay, so first off, before we get into this, let's just check a few things. So we have our assumptions here. First is SRS. This is good. We're told that we have a random sample of 1,280 students, so we're okay on the first assumption. The second assumption is X bar normal. Can I do that? Nope. Okay. So the second assumption is X bar normal. And we can say yes to this too because of the central limit theorem. So basically our assumptions in many ways are just drawing on what we learned last week about the sampling distribution of X bar. So our second assumption here is that X bar is normal and this is fine. And then the third assumption, if we want to consider this an assumption, is sigma known. And we can say yes to this too, because we are told that the standard deviation, so sigma, is 40,222. So we have those 3 points. Okay, so we're going to be using the z-score formula, which means that our interval is going to have the following form. We are going to have X bar plus or minus the z-score multiplied by sigma over the square root, or x bar plus or minus the z score multiplied by sigma over the square root of n. So this is what our interval is going to look like. Now we're going to compute this using Rcmdr. Okay, so there's two ways that we can do this. If we follow the stepwise procedure, the first thing that we have to do is work out the z score. So we're going to have z alpha over 2 is equal to z 0.10 over 2. Sorry, I should have mentioned this too. Okay, so we're going to have here we're going to have alpha. Where are you, alpha? There we go. Okay, so for the z-score formula, alpha is going to be 1 minus the confidence level as a percent. So we're working on a 90% interval, so alpha is going to be 0.10. So now our z-score is going to be z subscript 0.10. So that gives us z subscript 0.05. Okay, so now what we need to do is work out what this number is. So in lecture, what we would do is now turn to the normal table. But since we are working with Rcmdr, we can open our actual Rcmdr screen. So we're going to go R, library, Rcmdr. Okay. So now we will go distributions, continuous, normal. We want a quantile in this case. So normal quantiles. So we have mean 0, standard deviation 1, and we have 0.05 in the upper tail. So we can do 0.05 and click upper tail, or we can do 0.95 and click lower tail. That will give us the same result. With confidence intervals, we're always working with area to the right. So we're always working with upper tail value. So this would be a more direct way of computing the value based off of the actual form of the z-score. So we click OK, and we end up with the following. So here we're going to type just below under output. So here we're going to type equals 1.644854. Okay, so now on step 2, we're just plugging into our interval formula. So we have this. Okay, so then this is going to give us the following. So where x bar is, we're going to have our mean, which was 18,900, plus or minus the z-score, which is 1.644854, multiplied by sigma over the square root of n, which we worked out to be 1124.24. All right, so then we're going to have 18,900 plus or minus. Okay, and then we need to work out what this value is. So we can actually just go back to Rcmdr. So we can go 1.644854 multiplied by 1124.24. Click submit, and then we have 1,849.211. All right, and then we're gonna have 8900 minus 1849.211 to 18900 plus 1849.211. Okay. And then that should give us an interval of the following form, which I will boldface here, which is, 1 second, Rebecca, sorry, I just saw that. 17050.79, comma, 20749.21. Okay. So question, why in part A you wrote mean unknown? I wrote that the population mean mu is unknown because we have no information about it in the question. So there's nothing in this question 16 blurb that tells us what the population mean is going to be. The only thing that we could say about it is that it's the true or the population average amount of student debt for the population of interest, but we don't actually know what that value is. Yeah, it gets tricky in this unit. Okay, so that's part B, which is this computing the interval. So this is sort of the long way of doing it, which is going to be very similar to how we would do it in lecture and how you would do it on part A of the assignment, with the only difference that you're able to use R to generate the z-score. So we used R to find the z-score for this interval instead of using the standard normal table. Okay, in part C, we have interpret the interval. So this would be the third step of the interval construction process. So we can write here, we are 90% confident that the population mean amount of student debt for all students in the population of interest is between $1,750.79 and $20,749.21. Okay, so our interpretation of the mean is essentially, or of the confidence interval, sorry, is essentially composed of 3 parts. We have the percent confidence level that we are working with. We indicate that we are talking about the average of whatever the variable is we're measuring, so the average student debt. We indicate the population that we are talking about, and then we state the bounds of the interval. So we have, in this case, we are 90% confident that the population mean amount of student debt for all students in the population of interest is between $17,050.79 and $20,749.21. Right. Okay, any questions about those first 2 parts, or those first 3 parts rather? All right, the next few questions are all based off of, are all asking for essentially different interpretations of the confidence interval that we constructed. So what we're looking at now are some of the subtleties or some of the conclusions that we can draw when we use a confidence interval. Okay, first off, in part B or part D, it asks, does the interval contain the true mean, or does it not contain the true mean? Going back to the original conception of the explanation or the interpretation of the confidence interval. For an individual interval, we don't actually know if it contains the population mean. If we were to sample a high number of times from the same population, so say we were to collect 100 samples from this population and construct a 90% confidence interval for each sample. So we now have 100 90% confidence intervals in front of us. We could say, or we would expect that 90 of those 100 intervals will contain the true mean. But we do not actually know which intervals contain the mean and which ones do not. We would just expect that 90% of them do. So this particular interval that we just computed, we don't know if it contains the true mean or if it does not contain the true mean. What we can say again is that we are 90% confident that the values will be between what we calculated, but that word confident reflects the idea of repeatedly sampling and collecting an interval for each sample. In part E, we actually already worked out this calculation because we needed it for the Z-score. So it says for a 1 minus alpha % confidence level, we define a significance level that is equal to alpha. The confidence and significance level must add to 100%, or as decimals, they must add to 1. What is the significance level for this particular problem? So in this case, we would have alpha equals 100 minus 90%, which is 10%. Again, something that we already worked out. Okay, a friend wonders if the population mean differs from 20,000. What can we tell her based off of the interval? So we can say that at the 10% significance level, because that's the significance level that we worked at in this particular problem, since $20,000 falls inside the 90% interval. So if we look at the values of our confidence interval, we range from $17,050.79 to $20,749.21. So $20,000 falls within those two limits. So since it is within the limits, we do not have significant evidence that the mean differs from 20,000. So basically what we are saying here is that we are 90% confident that the population mean is between 17,050 and 20,749, which means that 20,000 is a plausible answer. Any value that sits in that range could actually be the true population mean or the population mean. So in part F, when our friend asks us, well, could the true average be 20,000? We could say that there's no evidence it isn't based off of the computation that we made, since 20,000 sits between those two numbers, between the bounds of the interval. In part G, same idea. So she then asks, well, could it be 30,000? 30,000 is outside the 90% interval that we computed. So we have evidence in that case that the population mean is different from 30,000. So in the part F, there's nothing to suggest that 20,000 isn't a realistic value or a possible value for the actual mean. But in part G, we have evidence that 30,000 would not be realistic because our interval is telling us that debt should be somewhere between $17,050 and $20,749. So 30,000, which is outside that interval, is not, based off of our calculation, a reasonable guess at the actual average amount of debt. Okay, and now part H, we're not going to work through because we haven't actually gotten to hypothesis testing in the lectures yet. Okay, so we'll come back to that at a later point. Any questions about 16 just before I move on to question 17? Okay, question 17 is the same as question 16, except that you will notice we now have the sample standard deviation rather than the population standard deviation. So we do not have sigma. So in this case, we're going to be using a confidence interval based off the t value. Okay, what do you know about the mean, standard deviation, and shape of the sampling distribution of X bar? Given the following information, why do we know that this has to be true? Okay, so we have, just before we get into this, a random sample of 1,280 students is taken from a larger normal population. Okay, so random sample from a larger normal population. That's an important sentence because it's telling us that the population is normal. So we are sampling from a normal population. Okay, what is the mean of the sampling distribution? We don't know. There's no information in the question that tells us what the population mean is. Same as in question 16. What is the standard deviation? This is also unknown because we don't have sigma anymore. So we now have little s, but we do not have sigma. What is the estimated standard deviation of X bar? Little s over, this is going to be little s over the square root of n, where little s replaces sigma. So 45,192 over the square root of 1,280 is 1,263.15. Okay, so we have an estimate of the standard deviation of X bar, but we do not know the actual standard deviation of X bar. What is the shape of the sampling distribution? It's a normal bell curve. Why do we know this is true? Because we sampled from a normal population. So the population that we took the sample from is normal. Therefore, X bar will also be normal based off of the definition that we established last week. Okay. So because the population is normal, X bar is normally distributed. And then because the population is normal, when we replace sigma with S, we have a T distribution. Okay, so these last two lines here, this is just a little bit of a theory recap from what was given to us in lecture. And again, all we're saying here is since X bar is normally distributed, if standardized, we have a z-score. Okay. So that's what that first line is telling us. And then on the second line, we're basically just saying, if we replace sigma with S, we then have a studentized random variable, which is a t-value. So basically, long story short, because we do not have sigma, because we are working with sample information only, the confidence interval will be computed using a t-value rather than a z-score. Okay, so let's calculate a 95% confidence interval for the population mean. All right, so our goal here, following the setup that I had above, I'm just gonna take the first few parts here, and then I will alter as necessary. So first thing we're gonna do, we know that sigma is unknown, so we're gonna be using a t-value. The second thing we were wondering is, was the population normal? And we know that this is true because the question tells us we sampled from a normal. So now in our formula, we're gonna have a t comma n minus 1, okay? And this will be an s. So the interval that we're working with now, because we do not have population standard deviation, is gonna be x bar plus or minus the t value multiplied by s over the square root of n. So it's a very similar formula in terms of like the components, but we're replacing the z-score with the t value because we replace sigma with little s. Okay, so I'm just gonna copy and paste this part down here. And then I can delete this for now. Delete this for now. Okay, so we have an alpha value of 1 minus 0.95, which is 0.05. Here we have a t on alpha over 2 n minus 1, which is a t on 0.05 over 2 and 1,280 minus 1. Oh, word. All right, so this is going to give us a t on 0.025 and 1,279. All right, so now what we have to do is figure out what this value is actually equal to. So we go to Rcmdr, we click distributions, continuous, and we go t distribution now. So in the first problem, we were using a normal. In the second problem, we were using a t distribution. So we click on t quantiles because we want a t value. We click upper tail and we have 0.025 because the way the value is read is the same as a z-score. So that subscript area is the value in the upper tail. And then we type in our degrees of freedom, which is 1279, and we click OK. And here's our output. Right. So now we can start plugging into our actual formula. So X bar is going to be 18,900. Oh, I don't want the bar. Plus or minus, and then here we're gonna have our t value, which we worked out to be 1.96182. Then we're gonna have little s over square root of n, which we calculated in part A. So that's the 1263.15. Okay. And now we're going to be in the same process that we had before. So we're going to have 18,900. And then we're going to go plus or minus. And then we're going to multiply these two values together here. So if we go to Rcmdr, we will have the following. Click submit. So 2478.03. Okay, and then if I add and subtract this, I should end up with 1641.5. 421.93 to 21378.07. Right? So very similar process to what we had before. Key difference, again, is just that we're using a t-value instead of the z-score because we're using little s in place of sigma. From Rcmdr, we can work out the t-value and we can work out the z-scores directly. The z-scores we've had lots of practice working out. That's what we did in week 5 and week 6. So last week we saw examples of this as well. The t-value is the same process as finding a z-score, except we have to input degree of freedom. Okay, so now we can rate, we are 95% confident that the average debt of all students that the population average debt, but the population mean debt of all students in the population of interest is between $16,421.93 and $21,378.07. So again, we have the 3 components of our interpretation. We have the percent confidence level we're working with. We have an indication of the variable and the population that we are dealing with. And then we have the bounds of our interval. Just like before, for the same reason, we don't know if this exact interval contains the population mean, but if we were to construct, say, 195% intervals from this population using the same sample size, then we would be confident that, or we would expect 95 of the 100 to contain the true mean, but we don't know if the individual interval does. Same rationale here as before. So what is the significance level for this test? It's just going to be 1 minus 0.95, or sorry, 100 minus 95%, which is equal to 5%. Okay, a friend wonders if the mean differs from 20,000. So we're going through the same sort of process that we had before. So if we look at the interval, we can see that 20,000 is contained within the bounds. So that means, again, that 20,000 is a plausible value for the true average amount of debt. So because 20,000 is inside the interval, we have evidence, or sorry, we do not have evidence that the population mean is different from this number. So there's nothing to suggest that it couldn't be 20,000. The interval contains 20,000, so that gives evidence that it possibly could be. The same friend wonders again if 30,000 is a plausible outcome for this interval. Since 30,000 is outside the interval, this would mean that we have evidence it's not equal to 30,000 because our interval is telling us it must be between 16,421 and 21,378. All right, any questions about 17? All right, if there's no questions, now what we're going to do is look at an example of how we can build confidence intervals in Rcmdr more directly. So the 2 examples that we just looked at, 16 and 17, I was basically just following the 3-step problem, the 3-step process that's established in lecture. Some lecturers might not use 3 steps, but basically just plugging into the formula with Rcmdr being used to find the T or the Z score. In 18, we're going to use Rcmdr to build the confidence interval directly. So we're going to use Rcmdr to find the interval and not go through those 3 steps. Now, that being said, we would still want to check the assumptions, and we will get to that point. Usually we're going to do that first, but for illustration, we'll start off with just how to construct the interval. Okay, so we're going to be using this Dr. exercise demo. So this is the data that's contained in the file. So if we go into Rcmdr and then we click data, import from Excel file. So this is going to be the doctor data. Okay, click OK. So now I just have to find it on my CPU. So I have Dropbox, document, lecture. All right, if I click view, I can see that I have that information that's given on the slide, okay? Oh, and there's only those 20 values. All right, we're gonna use Rcmdr to construct a 95% confidence interval for this data set. So to do that, we go statistics, means, single sample t-test. You can see here that there's really no other option. Okay, so we click OK. We pick our variable. Now you'll see here we have some questions about the population mean. For now, just leave it as two-sided. We'll get to that in the next unit. And then we're asked for the confidence level. We are building a 90% interval, so we're just going to change this to 0.90. So again, statistics, means, single sample t, 0.90. And then we click OK. All right, so here's our output for the question. Okay, now using this output, we are being asked to fill in the following table. So we have confidence level, significance level, confidence interval, sample mean. So we have a 90% confidence level, which means that we have a 10% significance level. The confidence interval is shown right here. So you can see that when we run that, we're given the confidence interval directly. Okay. And then the sample mean is given at the bottom of the output. So now what we can say is, so what is this data showing us? So this is their minutes of exercise per week of Canadian doctors. So we have in 2019 an article indicated that a large population of Canadian doctors reported a total of 281 minutes per week of exercise. We took a sample of 20 doctors and we recorded how much they exercise per week. So we are 90% confident that this large population of Canadian doctors exercise between 281.63 and 292.87 minutes per week on average. All right. And then we have at the 10% significance level, because 281 minutes is inside, no, it's just outside actually, is outside the 90% confidence interval, there is evidence that the average weekly amount has changed from 281. So notice it's actually very close, that the interval runs from 281.6 to 292.8. So 281 is actually just outside this confidence interval. It's just on the lower edge. So therefore we have evidence that the amount that doctors exercise is actually different from the amount stated. And in this case, it actually looks like it's higher since the interval is telling us that we're 90% confident that it's between 281 or 281.6 and 292.9 minutes per week. Okay, we have to state the assumptions of the test now. Again, this is typically done beforehand. The first assumption is that a simple random sample was collected from the population. The second assumption is that the population that we sampled from is normally distributed. All right, you can see that when we read the question, there's no evidence that the population mean is normal. There's no indication in the question. So when we read question 18 here, there's no indication that we actually sampled from a normal population. So we might have actually violated this second assumption. So we're not sure yet. So what we would like to do, and actually what we should do really before we compute the interval, but what we would like to do is check to see if this assumption, if there's any evidence that this assumption is true. There's a few different ways that we can do this. Basically, what we can do is we can follow through with what we did in exercise part B, question 2 on assignment 6. We can study the shape of the sample. So does it look like it's normal based off a histogram? Does it look like it's normal based off a box plot? If we were to run or build a QQ plot, does it look like that gives evidence of normality? So we'll use a histogram as an example. So here's a histogram of the data, and then we have to decide based off of what is given in this problem, whether or not this histogram appears to give evidence of normality. Okay, so the shape of the sample data for the doctor's minutes appeared normal. I would say that this does not appear normal. So this histogram does not look like a normal bell curve, in my opinion. Does not appear normal as the spike of the probability at the left side is too high. So basically just saying that this peak here, if it was reduced, that would look a little bit more bell curve-like. So this part here is too high. A sample size of 20 will give us some indication of the shape of the population, but ideally we would like to have a larger sample. So from 20, we're getting some indication of what the population will look like. That's fair, but the more we collect, the better. Okay, true or false? 90% of the doctors exercise weekly for the number of minutes between the endpoints of your intervals above. Okay, so this is false. Why is this false? This statement is implying that the interval is telling us the proportion of doctors in the sample that exercise between 281.6 and 292.87 minutes per week. The interval is not telling us the proportion of doctors that exercise between these times. The interval is telling us with some degree of confidence what the true population average amount of time exercised is actually equal to. Okay, so not telling us the proportion that actually worked out. The width of a 99% confidence interval created from the data above would be larger than the width of a 90. This is true. Why is this true? For the same sample size, so basically for the exact same sample, anytime you increase confidence level, you increase the width of the confidence interval. That's a fact. That can actually be shown very easily because basically the t value in this case is going to go up. So you're just multiplying by a bigger value in the margin of error. So that's going to push out the bounds of the interval. So this is, for the same sample, a fact. The shape of the population distribution is always the same as the shape of a test statistic distribution. This is false because, for example, if we collect a sample of size 50 from an exponential distribution or from a right skewed distribution, like we did on assignment 6. The shape of the test statistic distribution, which is actually just the shape of the standardized mean, isn't the same as the population. So if we sample from a right skewed distribution and we take more than 30 observations, then X bar is normal, which means that the test statistic distribution is also normal. We haven't actually talked about what the test statistic is in any capacity yet, but I mean, essentially, just for clarity, what this question is asking is the shape of the population the same as the standardized mean? Shape of the distribution of the standardized mean. And of course, the answer to that is no. That's what we spent all of assignment 6 talking about. That's central limit theorem, essentially. There is a probability of 90% that the true mean of weekly doctor's exercise minutes is in the 90% confidence interval created above. No, this is nonsense. Again, a confidence interval doesn't tell us anything about the probability of an event occurring. So this is just a nonsense statement. A 90% confidence interval created from a sample of 1,000 from the population of weekly doctor exercise minutes would have a greater chance of capturing the true mean of weekly doctor exercise minutes than the 90% confidence interval you created with a sample of size 20. Nope, this is also false. This is false because the percent confidence is exactly the same. So the only difference between confidence intervals at the same percent, so a 90% confidence interval with 1,000 people and a 90% confidence interval with 20, is that the 90% confidence interval for 1,000 observations is going to have a much smaller width. So the difference between the lower bound and the upper bound is going to be much smaller compared to the difference between the lower bound and the upper bound when the sample size is 20. 90% of all intervals created with this formula, with many, many repeated samples of the same size from the population of weekly doctor exercise minutes will contain the true mean mu of weekly doctor exercise minutes. Yeah, that's true. That's the definition of the confidence interval. So basically, this is just saying that if we computed 1,000 confidence intervals from this population using samples of the same size, 90% of those 1,000 would contain the true mean, and that's true. We expect that to be true. So this sentence is just reiterating the definition of the word confidence, which is something that we established when we introduced confidence intervals in the lecture. Today, we can be sure that the true mean is 281. No, this is false. Obviously that's false based off of what we just discussed, right? Okay, part E, we haven't done hypothesis testing yet. Okay, so that brings us to 19. So now we're going to use Allen's midterm data to create 2 confidence intervals. So let's just go over again how we use Rcmdr to build confidence intervals. So the first thing we're going to do is we're going to import the data. Right. So let's take a look at this. So we have participation and we have midterm. Okay, so we have 2 variables here. All right, so we are only going to be working with the midterm grade of these first 20 students. So hopefully Rcmdr will just automatically ignore those NAs. We'll find out momentarily. So we are going to construct a 95% and a 99% confidence interval for this data. So we'll have statistics, means, single sample. We select midterm in this case. And then we have a 95% interval. So we don't have to change anything here. We don't have to change anything here. And we can leave confidence level at 0.95. Click OK. Yeah, it ignored the NAs automatically. So that's great. And then we can paste this information in below as follows. Okay. Now we'll do the same thing for the 99% interval. So again, statistics, means, single sample t-test. And then we just change this to 99%. All right. So here are our two confidence intervals. Okay, now for each interval, fill in the tables below, and in each case, whether there is significant evidence that the true average score of all calculus students taking the midterm is different from 49.5. Okay, at the 5% level, we have the following midterm scores. So you can see that the average midterm score for the whole population of students is estimated to be between 49.9 and 55.0. The sample average for this test was 52.46%. So we can be 95% confident that the population mean grade for the calculus midterm for all students writing this test will be between 49.908 and 55.012%. It's kind of a trolling type of example given that we have a midterm this week, but it's a calculus test, not a stats test. So at the 5% significance level, because 49.5 is outside the interval, there is evidence that the true score is different from 49.5. Same idea as before. The interval is telling us that the score on the test, the average score on the test is somewhere between 49.9 and 55. So therefore, because 49.5 is outside that interval, that would give evidence that our score is different from that value. Okay, so now we can do the 99% interval. Notice here that the bounds of this interval are bigger than the bounds shown above. So one of the true false questions that we answered before was, will confidence level increase size of the interval? And that's true. So for the exact same sample, we moved from 95% confidence to 99%. And the result is that our interval increased in length. So the difference between the two bounds here and the two bounds here is, the difference here is larger than the difference here. And notice that the sample means are the same. So we can write basically the exact same thing. We can be 99% confident that the true population mean is between this and this, and then we just have to replace these values here with the values for our interval. So notice that the interpretation of the interval is very standard in that sense. We don't have to make a lot of alterations to it. In this particular case, it's exactly the same, except we changed 95 to 99%. Okay, in this case, since 49.5 is inside the interval, this interval gives evidence, there does not give evidence that the average score is different from 49.5. Let's just see what else we got. All right, let's work through these. Fully and completely state the two assumptions that must be met in order to perform this test. Those are the exact same assumptions that we worked out before, so we can literally just copy and paste here. Okay, and now we need to check to see if there's evidence that the second assumption is met. So part D is asking us to create a normal probability plot and then describe what we see. So when we're using t-based intervals, the normal probability plot will almost always be our go-to for assessing normality. So to do this, we go to Rcmdr, we click graphs, quantile comparison plot, we click midterm, and then we go to options. And then, so we'll have normal probability plots of midterm scores. Click OK. Here's our QQ plot. All right, so now we need to add this into our output. Okay, so we come back here. Okay, so what can we see from this normal probability plot? Well, we can see that the bulk of observations follow the straight line pattern that we'd hope to see. However, in each tail, we notice that there are values that deviate from that straight line relationship. This pattern is forming a kind of inverted S shape, which implies that the tails of this distribution are wider or heavier than the tails of the normal distribution. So we cannot say that this normal probability plot, let me see if no, let's see. Does not give sufficient evidence that the distribution, that the population is approximately normally distributed. Okay, so then we can say, what is the impact of this? The intervals we computed in part B are likely not valid, and therefore the results from said intervals should not be trusted. Okay. Yep, so we can say, yeah, that's a fair point. Note that observations 15 and 16 are flagged as potential outliers. Okay. All right, sweet. So that actually, those are the examples I wanted to work through based off the intervals. We did a lot of extra stuff today. We talked a lot about interpretation of the interval. We worked through those true false questions. I mean, one of the big things is that we can actually do a lot with a confidence interval, maybe a lot more than you might have expected based off of what has been discussed in lecture. The takeaways from today's lab, I think the most important things to keep in mind in terms of completing the assignment are how to actually build the interval. So there's two ways that we can do this. If we want to do it sort of a brute force way, we can use continuous distributions, normal or t distribution, and then we can use the quantile value inside those two distributions to find the t value or the z-score, and then we can basically just put the interval together ourselves. If we want to get R to build the interval directly, then we go statistics, means, single sample mean. And then all we have to do here is pick the variable that we want, and then the confidence level that we need, and click OK. And that will give us the interval inside of the output from that procedure. All right, so I'll stop here. I still have 10 minutes left, so I'll hang around if there's any questions and whatnot, but I will officially stop the recording.